This is Dr. Ravi, and we are going to cover the chapter number 5 of operating systems and concepts. This is the continuation of remaining part of course operating systems at Sukkur IBA Computer Science Department. And today we are going to see the CPU scheduling. CPU scheduling is one of the basic of multi-programmed operating systems, and it is done to make the clever switching between the processes, the multiple processes for getting the maximum work done by managing the time and to make the computers more productive. So in this chapter we will be seeing several concepts, basic concepts, and we will see several basic criteria. In concepts we will see some of the main things, like we will see what is the CPU burst and CPU burst, IO burst, right? What are these two terms? Some nomenclatures will be discussed in this basic concepts. Where CPU burst, IO burst, and scheduler and dispatcher, right? So these terminologies will be discussed in the basic concepts. Then we'll go to the criteria. What are the criteria of CPU scheduling? So we'll be seeing the quality of service parameters in this criteria, where we'll see that how much jobs has been done in a specific amount of time, and how much CPU was utilized, how these things are calculated actually, and we'll see these quality of service parameters. And next we'll move on to the algorithms. We have different type of algorithms. Actually we don't have one approach, but we have many algorithms for CPU scheduling. In this chapter we'll be discussing only some very key approaches, some key algorithms, very popular algorithms like first come first serve, and shortest job first, and also we see round robin, right? And we'll see some priority queues. Okay, then we will come to thread scheduling. Thread scheduling is also like that as previously as these first come first serve and these algorithms, but we will be seeing the thread scheduling by implementation example of p threads, right? That how the threads are scheduled. Actually in the recent most modern operating systems, the scheduling is the process in any operating system like Linux. If we get an example of Linux, then most of the processes in this are called threads, not the process at the kernel level. So we'll be talking about the thread scheduling. So you should make in mind that a thread is actually a process when we are talking about the Linux kernels. And we'll see multiprocessor scheduling. Now in multiprocessor scheduling, we have different type of things to discuss, like we have homogeneous processors. Maybe we have, which is not a real example, but we'll be seeing some ideal processes where more than one computers or more than one CPUs have exactly same configuration, right? Same configuration. And we'll be seeing some multi-core processors. So how the CPU scheduling would work with multi-core processors. Now in ideal process, this is an ideal situation. However, this is not the real situation, because if you have two different computers and they even have same configuration, exactly the same configuration, but still the performance of these computers might vary. And we have also multi-core processors where we have multiple cores within a single CPU, right? We will be discussing this also, and then we will see the multi-thread, multi-core, right? Multi-thread multi-threaded and multi-core operating systems, processors, right? Okay, so this is multiprocessor scheduling approaches. We'll see what approaches are being used in this, and then we'll move to real-time CPU scheduling. Real-time processes are actually the time-critical processes. Time-critical processes, right? Where time is very much necessary to consider. Means what is the deadline to complete a process. So this is a very critical thing to consider when we are dealing with the real-time systems. Now, the example of real-time systems, we can see that yes, the medical applications. Most of the medical applications are real-time application. If we see the compared equipments like ships and aerospace vehicles, then these are real-time systems. They should convey the information in real time. So these are time critical. If this doesn't happen, then there might be a big loss. So we say these systems are real-time and time critical systems. And then we'll see operating system examples for Linux and Windows and Solaris, right? And then we will see the methodology of evaluation. There are two methodologies actually discussed. That actually we will see deterministic modeling, right? Where we will be discussing queuing theory here, right? And this is actually a simulation approach that before going to schedule the jobs, we see how these will impact in real time, in real application, for real application. Okay, so let's start with this chapter. Now the main thing when we are discussing about the concepts of CPU scheduling, the main thing is a cycle of two processes. This cycle is composed of two components. The first component is CPU burst, right? And another component, here. The first component is CPU burst, and another component is IO burst, and these are followed by each other. Instance, the CPU burst will come, then the IO burst will come, then again the CPU burst will come, then again IO burst will come, right? So this is like working actually in a cycle, right? Maybe not like this, maybe like this, right? If we don't consider this, here is CPU and here's IO burst, right? And these are working in a cycle, so one followed by another. Now here we see the example, and this is actually a time, or maybe time taken by a process to happen, right? And this is actually a wait time where a process or the CPU is waiting, a processor is waiting for some input output, right? So here we see the example. Most CPUs are actually the process bound, and some CPU are actually IO bound. So this CPU is the example we have. We are waiting for some. We are working. The system is actually working to read from some file. The system is working in CPU burst, while in IO burst it is waiting for some input output, right? And again we have CPU burst where store increment index write to file, right? So this is here we are reading, and here we are writing, and again we are waiting for IO burst, and then we are loading some data to read from the file, right? And this is also a CPU burst where some work has been done, right? So CPU burst actually means that some work is being done, and the time taken by CPU for that is called CPU burst, while the time taken for input output is called IO burst. So these two things are some of the nomenclatures we need to consider when we are seeing this operating system, this chapter 5 scheduling. And a CPU, but sometimes CPU burst may be long, sometimes IO burst may be long, like here. Sometimes if we say this is CPU and this is IO burst, then we have an IO, then CPU, then IO, then CPU, then IO. We are going to IO and then CPU, right? So here we see that IO length is smaller than the CPU length, right? So let's say it is T1, right? So this is CPU burst. This is and this has some long time, and the IO has some small amount of time required. So we might have some large number of short bursts. Maybe we have many short bursts also, like this. Another example, if we see CPU and IO, right, then we might have long input output and short processing, long input output and short processing, long input output and short processing, right? So this is another example where we have this CPU work time is very small while we are waiting a lot for input output. So in such situations, when we are waiting for when CPU is waiting for some input output to come, how to efficiently utilize that idle time. Here actually your CPU is idle, right? So how efficiently we utilize this idle time is actually the key of this chapter, that how we manage the system, so that for suppose if we say there is one the CPU burst, and then we have IO burst, and we have some CPU burst, and then we have some IO burst, right? And this is maybe one process, right, for the one process. And same for the another process, when it's working on the CPU, we are waiting for some IO, and when it is waiting for an IO, we are working for the some job to done on the same CPU. When it's working for CPU, we are waiting for the IO, and something like things goes like that. The idle time is being utilized by another process. The same process is working in parallel, in maybe in concurrent basis, in concurrent way, where the time has been managed to do to perform the multiple jobs. Okay, so we have two components in this scheduling. The first one is CPU scheduler, and another is the dispatcher. So CPU scheduler actually selects from among the processes in ready queue. As we know that we have a ready queue. If we go to the cycle of the operating systems, as we have of the processes, as we have already seen in the process chapter number 3, that a new process is being generated, and it goes to the ready queue, right? It goes to the ready queue, and then a process is running, right, or executing, and we might have also a wait state, and then the process goes to terminate. Okay, so new to ready, and ready to running, and again running to ready, and running to wait, and wait to ready. So this is actually the system goes to wait state because of IO burst, and when it finishes, it is being terminated. Okay, so so we consider these all have some these states have a queue attached to them, right? A queue is attached to them. a queue is attached to them, right? So a process is running and it goes to ready, and again it goes to running. Actually from selection of from these processes is the work of a scheduler. A scheduler selects from among the processes in the ready queue and allocate the CPU core to one of them, right? So the selection of a process from the ready queue is the job of a scheduler, right? And the CPU scheduling decision may take place on four events, right? The first event is a switch from running to waiting state, right? When a job is running and goes to waiting state, right? And then CPU scheduling occurs, and also when switching from running to ready state, as we have seen here, when a job has been switched from running to ready state, waiting state and running state, and switches from waiting to ready, like this, from here to here. So waiting to ready state and then finally terminate. So these are four events when scheduler come into play. And these four conditions scheduler come into play, right? Come into play. Now scheduling under 1 and 4 condition. When job switches, when your CPU switches from running to waiting state and when it terminates. This type is non-preemptive. When we say some process is non-preemptive, it means it is uninterruptible. Uninterruptible. Uninterruptible means that no interrupt can stop this job to complete. This job is required to complete, then another job can be allocated to the CPU, to the processor. And so the first and the fourth are the non-preemptive conditions when a job switches from running to waiting state. It's a non-preemptive, right? Because it cannot be hold, right? And while all other conditions, with these two conditions, the second and third conditions, these conditions are preemptive. And these can wait. These conditions can go into wait. This job can be performed into different chunks. And for example, the one chunk has been performed now. Another chunk is going to perform after maybe 5 seconds or maybe 4 seconds. So after some time, you can again resume to that job. Here the PCB come into play. Where you save the state of job to resume in next phase. Okay. Consider access to a shared data. Okay, these are just some consideration. So we have already seen the main concepts. Okay. Another thing is dispatcher. Dispatcher is actually suppose here. Yeah. Now suppose here we have a job, a queue here, and we have maybe CPU here. So here we have a dispatcher, right? This dispatcher is actually responsible to dispatch the job to this service, means to the CPU, and in this CPU, okay, it actually transfer. We can say that it transfers controls of a process of a processor to a process. right? So a job of a dispatcher is to transfer the controls of a processor to a process, right? Now, when a process moves in here, then all the controls of this CPU belongs to this process, right? Actually, you may consider that the processor is a leading activity which once it occupies a core or a processor, then it releasing that process is under the control of this processor, right? So actually the controls of a processor are handed over to the process which is currently operating. Okay, now in dispatcher we have some latency involved. The time take for dispatcher to stop one process and start another, right? Or suppose there is one process is working and maybe this is the ready queue, right? And maybe this is the wait queue, right? So once this process has encountered some input output, need to get some input output, it may be pushed back to this queue, right? So the time taken for this and a new job assigned to that processor in the another time, right? This will be T1 and this will be T2. So this time T1 and T2 is actually the dispatch latency, where the switch between the process is occurred, right? So a dispatcher module gives control of the CPU to the process by selecting the short-term schedule. This involves switching context. As we know already, context switching, we have seen that how context switching works. In the processes, it is PCB which helps to switch the context from one process to another process. For your reminder, we have seen this in chapter 3. You can go to chapter 3 to see what is PCB. Actually, this is used to save the state of a process so that it can be resumed from the same location where we have left it. And from switching to user mode, actually we have two modes, kernel and user. And so a process is working in every user level process or thread is actually converted or mapped to a kernel level thread, right? And it has been assigned to a CPU, then again again going back to the user mode is actually also the responsibility of the dispatcher, and jumping to the proper location in the user program to restart the program, to resume the program, right? So for example, this is also done with the help of PCB, that you are resuming the job. So if we see here that how this dispatch latency is actually working, that process, for example, there is a process 0 which is already executing in the running phase of a process, and after as some input output or maybe some other priority or maybe for any reason it has to stop, then it will save its state in the PCB, process control block, and once the save is complete, it restores the state of the process 1 from the PCB1. This is PCB0 which belongs to process 0, and this is PCB1 which belongs to process 1. So the time taken for restoring the state from PCB1 is also counted, and once the P1 start executing, the dispatcher time is over, right? So from here to here, the time taken is actually the dispatch latency. Okay, latency means the delay. How much delay is involved when we are switching in between the processes, right? Now we have also some scheduling criteria. In scheduling criteria, we are seeing here some quality of service parameters. Right? We are seeing some quality of service parameter. Okay, so for example, we have a queue here and we have a server here. Now CPU utilization, that how much a CPU is busy during with a scheduling criteria. How we will calculate? We calculate this by seeing that utilization of a processor, how much time it was idle and how much time it was busy. So the key of scheduling is to keep the the CPU as busy as possible. Now theoretically this utilization might go from 0 to 100%. This is actually calculated in percentage, right? So theoretically this might go from 0 to 100%. However, in real situations, this may be not go to 100% every time. Maybe some spikes happen, but most of the time we can see 40 to 90% utilization for a good scheduling. Okay, and this is not a criteria, but this is what the real observation, right? Real observation that a CPU scheduling, even if we have a very clever scheduling algorithm with clever scheduling, we can go a constant utilization of 100% of any CPU. Okay, and if you see, if you want to see this, then you can see. I think in any Linux systems, if you use this command top, right? This is actually Linux command. On Linux and Macintosh, you can, if you write the top command, then you can see that how much CPU is being utilized by any application, right? Yeah, I can show you. Well, if I switch, then this screencast might stop. So well, you can experiment this. You can try this command on your Linux systems. When you write top, you will see the processes are displaying and how much CPU utilization is over there, right? So CPU utilization is one of the key to consider or to measure when we are talking about the quality of service parameters. Okay, and another thing is throughput. Throughput is actually that how many jobs are being thrown. This is, let's say, terminator. This is maybe a source, right? This is source, this is terminator, and this is CPU, and this is queue. So we'll see that how many jobs are arriving per second per unit of time, right? So maybe process is completing 5 jobs per second, right? So this is throughput. Okay, so this is a time bound thing. Number of processes that complete their execution per unit of time. For example, 5 jobs per second. If we are getting here 5 jobs, maybe this is terminator, or maybe we can have another queue, but whatever, how many jobs we are getting at the end of this server. Okay, and then another thing, we have turnaround time, the amount of time to execute a particular process, right? It is from the point of view of a process, the time taken from submission to completion. Actually, the time taken from submission to completion. Okay, so the job is submitted maybe at the clock of 10 seconds. When it was 10 seconds, let's say we start at sometime 10 seconds, and when it moves to queue and CPU and it is completed over here, maybe the time was 50 seconds, right? So 50 minus 10 is 40 seconds. 40 seconds is turnaround time, the amount of time to execute a particular process. Okay, sorry, it is not from here, it is from here to here, right? Maybe 30 to 50, maybe 20 seconds, right? So from submission to CPU to completion is turnaround time, right? And waiting time, the amount of time a process has been waiting in the ready queue. Because, for example, this is ready queue, and how much time a process is waiting. In this example, if we see, then it is waiting for 20 seconds. Okay, so this is the time is spent in ready queue actually. Time in ready queue. Okay, and then we have also response time. Response time is actually when you receive the first time response, which means when you started to attend, right? To get the attention, when you see the first call, it is not about the completion of process. It is for the response, first response. This maybe a process has maybe it requires many input outputs, right? So many times it goes to wait, and many times it stores its state to PCB. But we are talking about the very first process, the very first response, that when it was first time attended, how much time was there. So submitted to first response, right? The time it takes from start responding, not the time it takes to output the response. Okay, so when it start responding, right? When it has started to get the response. So these are quality of service parameter, and these are very much critical whenever you are working on scheduling of any system or any operating system. And furthermore, please note down that this throughput and CPU utilization, we always want to maximize the CPU utilization and maximize the number of jobs done in a unit of time. For example, if a system is completing 5 jobs per second, then if we make that system to complete 6 jobs per second, this system is better, right? And why these times, the turnaround time, the wait time, the response time, first response time, we want to minimize them, right? We want to minimize the total completion time, we want to minimize the queue time, we want to minimize the first response time. So we want to minimize the times, and we want to maximize and the CPU utilization and the throughput. So the optimization criteria are, as I have already told, to maximize the CPU utilization, maximize the throughput, while minimize these times. Now we'll be seeing the algorithms. What are the algorithms? So So these are actually algorithm part, scheduling algorithms. We are starting scheduling algorithms, right? So the simplest one is first come first serve. In the first come first serve, now suppose that this actually is this is a queue, and here is the server. It's not like that. It is actually like that from here to here, right? This is the flow direction. So in this queue, first job submitted was P1, then P2, and then P3 is submitted. So P1 has a length of 24 time units. Any time, this is time unit, right? Oh, sorry, this is actually the time unit for the CPU burst, time for CPU burst. CPU burst time, right? So the time unit may be seconds, or maybe millisecond or microsecond, whatever. But this is some time unit, okay? So this process requires 24 unit of times to complete, and P2 requires 3 unit of time to complete, and P3 requires 3 units of time to complete. Now what we have to do, what we'll do, we'll see that how much a process is waiting, average wait time. Now for suppose this job was submitted and it is started to get served, right? So the waiting time for P1 is actually 0. It have never it is not waiting, right? It is submitted and it goes to the service. It has got the allocation of the CPU. So P1 is waiting for 0 time, while P2 is waiting for 24 unit of times, right? And while P3, now the length of P2 is actually 3. This need 3 seconds to complete, this need 3 seconds to complete. So the length of P2 is 3 seconds, 3 unit of time, then 24 plus 3 is 27, right? So if we add them, right, and if we divide them by 3, then it is 70. So waiting time for this, average waiting time for this approach is 17 unit of times. For example, we can, for simplicity, we consider this as seconds, okay? So for 17 seconds, this in this approach is the average waiting time. While if we see the individual processes here, then we see that P2 and P3 are actually the smallest processes, smaller processes than P1, but still they are waiting for long. Maybe if we say that another P4 has arrived and it is only up to 31, only 1 unit of time, require only 1 unit of time, and maybe we have another only 32. Now these two guys are waiting for long, maybe for 30 seconds, to get done their job for only 1 second, which is only long for 1 second. So the first comes first most of the times in the distribution of or maybe scheduling is unfair in first come first serve. Now if we see that suppose that the jobs arrive in this order, where P2 arrives here, P3 arrives, then P3 arrives, and then P1 arrives, then what happens that the P2 has to wait, P2 has to wait for, P2 has to wait for 0 unit of time, P3 has to wait for 3 unit of time, while P1 has to wait on 6 unit of times, right? 6 unit of time. If we divide by 3, then it is 3 processes, right? So to take the average, we divide this, then it's 3. Now in previous example we have seen the average wait time was 17. Only by shuffling the order we can see that the time has minimized from 17 seconds. Now the average wait time is 3 seconds. So much better. In this we can say that this is much better than the previous, but we cannot guarantee that shorter jobs will arrive first and the longer jobs arise next. Actually, this effect which we have seen in previous is called as conveyor effect. A conveyor effect. The conveyor effect is actually we know we are living in a country where if a prime minister is coming, maybe here's a place or maybe a road or maybe a market, a prime minister is coming and usually people walk through this place, but if prime minister is coming, this walkthrough is blocked. Okay, so this might take 1 hour to come, but still these guys are waiting. So maybe a conveyor is coming, right? And but the shorter job has to wait longer. This is, let's say this is short job, and these are some variable sizes of the size of this box represents the size of a job, a process. So the shorter job has to wait for a long time, is a conveyor effect. Okay, and to cope up with this challenge, we have another algorithm. It is the shortest job first. In shortest job first, what happens that the short job is bring to the CPU first, and then the longer job goes to the next. Okay, so associate with each process the length for the length of its CPU burst, how much CPU it requires, how much time it requires to complete its job, right? So it depends on the CPU burst, how much CPU time it needs. The distribution is done on the CPU, on the basis of the CPU burst. Use the length to schedule the process with the shortest time. SCF is optimum, gives minimum average time. Gives minimum average time, as we have already seen in previous example. If the jobs arise in the inverted order, P1, P3 and P2 arise first, before then P1, then the average waiting time is minimized. But the difficulty is knowing the length of next job. How long the next job will come. For example, we can know that, okay, maybe this is the queue, okay, and this job is maybe 5 unit of time, this is 8 unit of time, this is 2 unit of time, and this is 3 unit of time. So we know that we have to take this first, then this, then this, and then this 8. Okay, but what about the next job? How long it will be? It will be 10, or it will be 1, or it will be 4. Maybe it should come before this job. So we don't know. We don't know that how long the next job will come. So this is the one of the challenge, and there are some approaches to this challenge also, to cope up with this challenge also, and we will see those approaches also. As we have already seen that P4 is only 3 unit of time, and this requires okay. If we see here that P1 arrives at 6 unit of time, and 8 unit of time, and 7 unit of time required, and 3 unit of time. So this will go first, and this will go second, and this will go third, and this will go fourth. So first is 4 and second, okay, like the same series, right? So with the length of the bus time, we decide which job will go first, okay, and if we calculate, then for these jobs the average wait time is 7. Okay, now how we'll determine that what would be the length of next job? This is a challenge, okay, to determine the length of upcoming job in advance, right? And to predict, to guess, actually, to guess or predict, or maybe guess that how long the next job will be. This estimation has several approaches, right? And it is dependent on two parameters, actually, two parameters. The first one is actually in the process size, and the second one is process type. The process size and the process type. The process size is actually the size of a process. Let's say a process is maybe 80 kb, right? And it requires 5 unit of times, right? And another process is 82 kb, right? Then we can estimate that it will also take 5 unit of time in time unit, okay? So even if it's 82, but we know that if 80 kb job is taking 5 unit of times, then 82 kb will also take 5 unit of time. But this is a size parameter, but this is not full and final, because the type of job may be different, right? The type of process may be different. So if this takes 5 unit of time for 80 kb, then this might, for 82 kb, this might take 10 unit of times. I'll give you an example. For example, if you are going from Sukkur to Islamabad, okay, now the distance is nearly 950 kilometers in between these two cities. Now from Sukkur to Islamabad, if you go by a public transport, a bus, then it might take 18 hours. Okay, if you go by your own vehicle, then it might take 9 hours or 8 hours by own vehicle. If you go by flight, then it might take 1.5 hours, I mean 2 hours. Okay, so not only the distance, but also the mode of transport matters. So here is the same situation. Not only the size, but type of a process, a job is also keeps account when we are determining the length of an job. Okay, so there are several approaches, from simplest to maybe difficult, but we will be seeing only the simplest, some of the simplest. If I suppose P1, P2, and P3, P4, and P5, okay, now this takes T1, T2, T3, T4, and T5. We add these times, okay, and divide by the total number of time. The average time is actually expected length of the next job. For example, some application is running, maybe you are running some MATLAB programs, and you are working on some maybe your code is running on the MATLAB and you are also listening some audio sounds, and maybe you are also browsing. So these three processes are working, and you are working on these three processes for maybe next 1 hour. Then one thread. Actually, keep in mind that when I am talking about the process, a process here I am considering a general term which can be used for a thread or for a process, whole process. So don't make confusion. Okay. So maybe the MATLAB and the audio jobs, and also your browsing patterns have the same average. Have the same average for 1 hour. If you are working on these three applications simultaneously, then you can actually predict. So at some extent, this approach works. But in many other approaches, this approach doesn't work. So we have also an exponential averaging also. This is a simple average. Simple average, and we have also an exponential average. We are keeping the average count of every previous job, right? So this is the exponential average. Okay, we see this is okay, CPU burst, and this is the case, right? So in exponential average, actually we are averaging of every previous process. This is exponential average. Okay. So here's some example. You can see these examples, and okay. Now here we'll see that how another variation of shortest job first is shortest remaining time first, which means that uh, the arrival time. For example, a job is arriving and the jobs arrives in a CPU on different times. Until now, will not be considering the arrival time, that when a job has been arrived. For example, in previous example we have seen that a job arrived with 6 bus time, 8 bus time, 7 bus time, and 3 bus time, and we have not considered time here, that when these jobs were arrived. Now in this we are also considering the arrival time. For example, P1 arrived at 0 time, and it has the bus time of 1, and P2 arrived at time 1 and it has bus time of 4. Now here if we see here that P1 has arrived, this is actually P1 has arrived at 0 time interval, and P2 arrived 1 and 2 and 3. These are time intervals when arrival times when the jobs were arrived, and these are the bus time. Now for suppose if I say that first P1 will go, then P2 will go, then P3 will go, then P4 will go, then P2 has to wait the P1 time minus the arrival time, so it has to wait 7 seconds, and P3 has to wait in this 7 plus this 8 plus 4 minus 2. Okay, this 8 plus 4 minus 2, right? So it's 10 for 10 seconds, and P3 has to wait 8 plus 4 plus 9 and minus 3. 8 plus 4 plus 9 minus 3, because it was arrived at 3 seconds. So the wait time for this job is maybe how much is 17 and 21 and 18, right? It has to wait for 18 seconds. Okay. Actually, sorry, this is 0 wait time for this, and 1 wait time for this, and 2 wait time for 10 wait time for this, and this is for this. Okay. Now, if we apply the preemptive shortest job first, then preemptive, as we know that preemptive means that a job can be interrupted. A job can be interrupted, right? Interruptible job. So P1 was working, it arrived at 0 time and it started working. It was working for 1 unit of time, then P2 arrived. We can say that arrival time of P2 is 1. So when P2 arrived, the length of its job was only 4, while the remaining length of this job was still 7. So the CPUs decided that this is the shortest job, so this job went into this was actually paused, and the CPU started working to this job, right? And this is the working job. So when it reaches to second 2, right, 2 unit of time, then another job P3 arrived, which requires the 9 unit of time, while this has been already working, and it already worked for maybe 1 more second, and the remaining time for this job to complete was 3. Okay. And but for some time, okay, the remaining time for this job was 3, and this time was longer than this 3, so it keeps on executing. When this P2 completed at time unit 5, then P4 was already arrived here, right? Was already arrived here, and P4 was completed for 5 seconds. Then this P1 was only for 7 seconds. It was selected for completion, and then P3, which requires 9 units of time, it was selected. So the average waiting time for these jobs is calculated like that. Okay. So if we see, then response time minus start time, right? So the P1 was actually it started here, right, 10, and it has already completed. It has to wait for some time, right? And the served time, this is actually the start, when it was started and how much it was served. So it was already served for 1 second, and then it was resumed at 10th second. So it has to wait for 10 for 9 seconds, right? For 9 seconds. And while P2 arrived at 1 second, arrived at time 1, and it started job at 1, so it has to wait for 0 time. While P3 started to work on 17 time, and it was arrived on time unit 2, so 17 minus 2 is 15, right? Yeah, these all. And P4 okay, started to work on 5 unit of time, and it was arrived at 3, right? So 2. Okay, we add these all and we divide them by 4, then it is 6.5. Okay, so this is the example of shortest remaining time first.